Hello everybody, my name is Michael Poat, and today I'm going to be discussing enabling high availability service with oVert Virtualization and CephFS. To start with the outline, I'm going to talk about the motivation behind this work. I'll talk a little bit about oVert Virtualization and CephFS, some of our plans on how we're going to use oVert, the deployments, different type of deployments with oVert, a few details on live migration and high availability, and then I'll conclude. So the STAR online computing environment has been generating large demand for high availability service. The STAR experiment, which runs 24/7, 6 months out of the year, if there's any downtime, it could cost big money. Our current deployment of our critical services is on bare metal, and this creates a problem if the fundamental hardware were to go down or a power outage. Typically, there's manual intervention is involved. So if we were to move to a virtualized environment, what would we gain? So virtual machines are mobile, and it can easily run on multiple hardware as long as the CPU architecture is the same. It can easily take virtual machine backups, clones, snapshots, etc. It can easily grow or shrink the size of your virtual machine, especially if you use thin provisioned virtual machines. KVM virtualization has a proven track record to be very stable, and virtual machines can be stored and accessed from a common storage, such as CephFS. Ceph is a distributed storage system which is based on RADOS, Reliable Autonomic Distributed Object Store. STAR, which is us, we have deployed a 30-node, 220 terabyte CephFS cluster with replication 3. We've done many studies with CephFS in the past and different Ceph configurations and feature testing. We have a few past publications shown here. CephFS, in our experience, has proven to be very stable, and it provides a common storage medium for our online infrastructure and users. So our plan forward would be to leverage CephFS as a main storage backend for a virtualization cluster, which brings us to oVert. So oVert is an open virtualization management application. It's based on Red Hat Enterprise Virtualization. oVert is the open source version. oVert is also the upstream project. It has new features in development. And what's nice is oVert leverages multiple storage technologies such as CephFS, GloucesterFS, and other POSIX file systems. Within oVert, there's two main components. We have the oVert engine, which is technically the brain of the operations. It manages your hosts and virtual machines. It offers a nice GUI web interface and has the ability to monitor your resources and manage your storage and CPU quotas. The oVert hypervisors, on the other hand, are the worker nodes. These are the machines that actually run the virtual machines. They can intuitively migrate the virtual machines from one hypervisor to another, and there is support for high availability with proper hardware. So our plan to use oVert, we would essentially like to create a resilient oVert cluster with no single point of failure. We would reuse some of our oVert provision nodes with the proper hardware requirements to deploy many high availability VMs. Ensure that power management is properly enabled with UPS backup power. We would leverage our CephFS distributed storage to store and access our virtual machines. And we would like to use the self-hosted engine feature, which I'll talk about on a future slides. So our first target use case would be our web server. So our online web server is a critical piece of infrastructure during RIC runs. We're looking to implement an identity provider for single sign-on. An IDP needs to be on at all times. If it goes down, new logins can't happen. And we'd like to deploy a few database servers as well. So for a standard deployment, oVert deployment, it typically looks something like this. This is sort of our newer test cluster that we've recently deployed. So we started out with 3 physical machines. One machine is the oVert engine. You'd go through this nice, simple deployment. And once the oVert engine is set up and all its bits are installed, you can then deploy your hypervisor machines through its web interface. Once you have your 3 machines set up, we then mount CephFS as our storage. So this CephFS will be our main storage domain where all the virtual machines and its data will be stored. So basically we created a few directories, one for ISO image files and one for the data domain, which is used to store the VMs themselves. Well, once you've come this far, you can then deploy your 3 virtual machines. So in our case, we have our database server, web server, and IDP server. And these 3 machines, virtual machines, can run on either oVert 1 or oVert 2. But there is a problem with this configuration. And that is, if the oVert engine machine were to go down, which is the brain of the operation, all the VMs become headless. So there's no control over them. You lose the failover mechanism. And if this machine were to suffer a more catastrophic failure, hardware failure, etc., it would be quite difficult to recover our oVert cluster. So it's not really truly highly available. But fortunately, there is another solution. So there is a feature in oVert called the self-hosted engine. Now, try to follow me. But a self-hosted engine is a virtualized environment in which the oVert engine software runs on a virtual machine on the host managed by that engine. So say what exactly? So think of it this way. You have a physical host that runs a virtual machine, and on that virtual machine you install the oVert engine software. Then this virtual machine will then come back and manage this host to run more virtual machines. So what's required for this? So you need 2 or more physical nodes that both run a software called the oVert High Availability Agent and the High Availability Broker. And these 2 nodes will negotiate using the High Availability Agent to determine which node should run the virtual machine based on an internal scoring system. And the scoring system is based on memory usage, CPU, how it negotiates, and the machine that has the highest score gets to run the VM. There is one caveat. So the self-hosted engine does not have Ceph support. Now, it doesn't have Ceph support entirely. It's just that the self-hosted engine virtual machine itself cannot be stored in Ceph. There are other available options, GlusterFS, iSCSI, pretty much all the other options it supports except for Ceph. But the next best thing for us would be a replication-3 GlusterFS file system. Think of it as, for those of you who are unfamiliar, think of it as an NFS storage replicated across a few machines. So GlusterFS is a scalable network file system. It's open source, redundant, POSIX compliant. It works quite well. But we're not going to make a huge GlusterFS, just one large enough for us. So we took the 2 hypervisor nodes plus a spare node, 3 disks per node, and we created a small 9-disk replication-3 GlusterFS setup. And until oVert supports CephFS for the hosted engine storage domain, GlusterFS will provide the redundancy that we need. So this is how a self-hosted engine oVert deployment looks like. So we start out with 3 physical machines again, and these physical machines all install Gluster on them, and we create our little replication-3 3-node file system. We also mount GlusterFS on oVert 1 and oVert 2. Once you have your storage domain created, you can then deploy your oVert engine VM. So this virtual machine, you start out with the oVert agent and the broker installed on one machine. Allows you to deploy this VM, and it does the whole setup that it requires. Once set up, this VM comes back to install additional packages to run more VMs, and it manages VDSM on both oVert 1 and oVert 2. Now, we're still going to use CephFS as our main storage backend for all the other storage uses. So once we have our nice oVert setup, we bring CephFS back in. And then we can run our 3 famous virtual machines, the database server VM, web server, and IDP. So if we try to break this setup, if we were to lose our storage node, for starters, well, don't worry. Gluster, which was running on these 3 machines, will continue to run with replication 2. And the oVert engine VM, which is stored in GlusterFS, wouldn't know anything. It wouldn't skip a beat. In a different scenario, let's say we were to lose oVert 2. Now, this machine was running the VM web server, and the IDP VM. The oVert engine here would recognize that this machine is down. It would ensure this machine is down, and it would notice the VMs are down and restart them on oVert 1. In a similar but different scenario, if we were to lose oVert 1, which this machine was running the oVert engine VM and the database VM, well, the first thing that would happen was oVert 2 would recognize this VM is down with the agent and the broker. It would restart this VM on oVert 2, and once it's back up, it'll check for any other down VMs and would restart our database server. So essentially, no single point of failure. To talk a little bit more about live migration. So live migration is a feature of the KVM hypervisor that allows you to transfer a live virtual machine from one hypervisor to another with practically no downtime. So the VM remains powered on and user applications continue to run during the relocation. The virtual machine's RAM is actually copied from the source machine to the destination. What's required? So the VM must be accessible from both source and destination hosts, so they're both reading and writing from CephFS. And there must be available resources on the destination host. So what we did, we created this little small PHP CGI web page with a multi-step web page. So the first thing that we did is we had filled out page 1. So we did the first entry, which we put ACAT, and we hit next, which would then bring us to the second entry page. But before we enter anything in here, we migrate the VM from one machine to another. Once the virtual machine is migrated, we then enter our second entry. We click Done, and the result is that it carries over the entry from the first entry to the second entry, and it's carried over. So essentially, we did a little test with HTTPD, and the VM does carry the RAM properly. To talk a little bit more about high availability. So high availability is a feature in oVert to ensure your VMs are always up. So what is required is that you must have power management enabled and with the use of a power fencing device. So on most modern servers nowadays, there's an extra network port in the back, which is for an iDRAC or IPMI interface. And this allows you to have a dedicated network link to the baseboard management controller. So you can modify the BIOS or restart the machine if there's any kernel panics or you can't access the machine even from a console. So you must have this enabled, and oVert must have access to this network port. So we add an extra network link. Additionally, there must be available resources on the destination on your destination host if you want to have in a failover event. And all your hypervisors must have the same CPU architecture. So we did a small 5-second power loss test on a host that was running a virtual machine. So what we actually did is run it behind the node, and we pulled the power, waited 5 seconds, and plugged it in to see how oVert would respond. So the first thing that happens is the oVert engine immediately recognizes the down VM, and it tries to restart it on another host. Additionally, the oVert engine will check the status of that physical machine, and it uses the IPMI interface for a status check. If the status of the machine is alive, but it's down, meaning its OS is down, but it can interact with the machine, it will restart the machine via the IPMI interface. Meanwhile, while it's working on restarting the machine, the VM should be back up within less than a minute, or however long it takes for the VM to come back. And within about 3 to 5 minutes, this physical machine will come back up, and everything should be back in oVert and nice and happy. So to conclude, the oVert virtualization will enable STAR to create a truly highly available system with no single point of failure. While high availability does require resources on standby, you must have 2 times the CPU and memory available. I think it's a fair trade-off to ensure that our critical nodes and services are always up. In oVert, we can easily add and remove hypervisor nodes, and with live migration, we can take hypervisor nodes out for maintenance with zero interruption. This does allow us to have a good use of CephFS storage for our virtual machines. So currently, we massively use CephFS to store content, our web content, user content, etc. And with thin provision virtual machines, we can create a small storage footprint by keeping the VM small and have all the content off the virtual machine, typically stored in Ceph. The self-hosted engine feature is a true high availability setup, removing single points of failure. The current trade-off is that this machine cannot be stored in CephFS. We do actually have a Red Hat feature request open now for CephFS support for the self-hosted engine. And lastly, virtualization will allow STAR to better use our over-provisioned physical nodes to deploy a nice set of VMs for our operational needs. Dan, thank you.
So one question is, you said you tried a 5-second power down on one of the hypervisors. Have you ever done a 5-second power down on your networking? What happens if the networking goes away to your cluster pool?
So it would be as if we would lose everything, essentially. So it would be the same thing if we had a network loss to our whole network, in-house. Whether it's a VM or a physical machine, we still would lose everything.
You would then see things like cluster additions and stuff.
Right. So in our little 3-node CephFS, we couldn't lose more than 2 nodes. If you were to pull the power, let's say the network cable out of the back of the machine, on oVert 1, let's say, the oVert engine would respond in the same way as if you pulled the power. It would try to power fence it, and if it can, it would determine that it's down, can't communicate, or and then it would fail over to the other machines.
Yeah, thanks for a very nice and clear talk. I see that you use Ceph as a backend to store the VM images.
Yes.
So you have tested 3 virtual machines so far. No scaling tests because Ceph. I mean, IOPS is not an issue there, or?
So that's a good question. So right now we have 1 gigabit links from our client, so that is clearly going to be a bottleneck. We have done a lot of testing with multiple clients into CephFS, and the performance does scale. We are looking to upgrade the client side to 10 gigabit because we know that there is a bottleneck with a lot of chit chat. If you're all your VMs are stored in Ceph.
Because we have done tests, and what we've experienced is that it's difficult. So one tricky thing if you have a lot of VMs is to guarantee a certain number of IOPS per VM if you run against a shared storage. Because I mean you don't need a lot of IOPS for the typical application, but you need to guarantee some 50 or so per guest. That's it, between 30 and 50. Otherwise you will. I mean it's very workload dependent. So I was interested how this works with Ceph, which is not a typical use case for Ceph. No, Ceph is meant to store large amounts of data for sequentially.
If you mentioned that you have higher links, so if you think about higher link connections, 10 gigabit or so, do you think that IOPS or that Ceph is dropping down the performance, or what's your estimation?
So we do know that we can run. I do have the number. There is clearly a limit with our CephFS cluster due to the only 30 nodes, and there is a number that we have, but we know that we shouldn't reach it with the current number of VMs that we're running. But if you do reach a limit, if you increase the size of your CephFS, your Ceph cluster, it should be able to handle the load.
Second short question: did you try the erasure coding or
in CephFS?
CephFS, yeah.
So we did look into erasure coding, but we did not see any performance benefit. It's more of a storage capacity benefit with erasure coding. But we did try all the other built-in features within Ceph, and due to our disks, and we're trying to use SSDs, we found that the actual standard drives work the best within Ceph.
Okay, thanks.